and we are back in Module 4 for the second video, so video 4B. This one's going to start on page 106 of your textbook. Classifying changes that occur in matter. So we're getting closer to being able to talk about chemical reactions, which I know you are all just as excited about as I am. But first, we are going to discuss two types of change. There's chemical change and there's physical change. Okay? A chemical change is a change that affects the type of molecules or atoms in a substance. So the type of molecule actually changes from beginning to end of this change. For example, eating a piece of cake. Okay? When you eat something, your body is sending in different acids and things to break those molecules up and actually change the molecules of your food into energy. So that's an example of a chemical change. A chemical change is irreversible. So once you eat the cake, it is eaten. You're not going to get it to come back up looking like a piece of cake. Sorry for that awful mental picture. The other type of change is a physical change. This is a change where the atoms and the molecules stay the same. So something happens to them, but their actual structure, the actual atom, the molecule, does not change. For example, cutting a piece of cake. Okay, so two molecules might have been really close together when it was together as one big cake. When you cut the cake, the molecules move apart from one another, but they still stay the same. So for example, cutting a cake is a physical change, and that is reversible. You can put that piece of cake right back in there next to the other molecules. More examples of physical changes would be phase changes. All right, phase changes are when a substance is changing from a solid to a liquid to a gas. And these are all physical changes. They can be reversed. A gas can turn back into a liquid. This is called condensing. Or the liquid can go back into and become a gas again, which would be called boiling. When a liquid becomes a gas. Okay? Or the liquid can go back to becoming a solid, which is called freezing. When a liquid becomes a solid, it is called freezing. When a solid is heated and becomes a liquid, that is called, you got it, melting. Okay, so phase changes, these are phase changes. Phase changes are physical changes. The thing that is changing in a phase change is the volume that the substance takes up. Let's write that down. In a phase change, there is a change in the volume that the substance occupies. There's a change in the volume that the substance occupies. A solid occupies the least volume. A solid of a substance occupies the least volume. Okay, a liquid of that substance would occupy a little more volume, and a gas of that substance would occupy the most volume. Okay, now I like to think about this in the volume in terms of people. It just helps me remember it, okay? So when we are really cold, we want to gather together and we want to squeeze together to try to keep warm, right? So just like a solid you occupy the least amount of volume. You have all these people in the room and you kind of group together to stay warm. That's your solid phase. Then liquid, a liquid becomes a little bit warmer, so you spread out, you're comfortable, right? You're chatting and talking with one another and everybody's at a fine temperature. You're occupying a little bit more volume than you did when you were really cold as a solid. Then as a gas is the hottest, right? And when we're really hot, we tend to say, oh, back up, stay away from me, children who are trying to sit on my lap. I'm way too hot for this right now. And you're trying to occupy the most volume that you can to try to air out a little bit. So I like to think of the amount of volume that a substance occupies in terms of phase changes, just like people. And hopefully that helps you a little bit too. Okay, now for something to really blow your mind. Did you know that solids, which are of course made up of atoms and molecules, those little atoms and molecules that make up any solid that you are looking at right now, okay, perhaps your computer screen, is made up of atoms and molecules which are actually in constant motion. They are constantly moving like this. But no matter how hard you try to focus your eyes on a solid, trust me, you are not going to be able to see it moving. Why? Because atoms and molecules are so very, very, very tiny, and they're just packed in so closely together that they are moving actually billions of times per second, and they're barely moving at all, but they are moving, okay? But for one atom that moves this way, there's another atom that's moving the opposite way, and so you don't actually see your computer screen moving back and forth because the solid stays the same. The atoms and their forces of moving back and forth kind of cancel each other out, okay? This is the kinetic theory of matter. Kinetic has to do with motion, and the kinetic theory of matter says that molecules and atoms are in constant motion, and the higher the temperature, the greater their speed. Okay, so let's draw a little picture here. Say this is kind of going to be like figure 4.4 in your book to help you understand, okay? Here's a solid down here. We're just going to draw like 8 atoms or molecules that are close together, okay? Here is the substance in its solid form. As you can see, it occupies a small amount of volume at the bottom of its container. There it is just sitting there, right? And the temperature, we'll say, for this substance is room temperature. So these molecules are actually moving back and forth. You can draw teeny tiny little arrows, but you can't see that the solid is actually moving, okay? Now, when you increase the temperature, think about humans, you increase the temperature. To increase your temperature, what do you have to do? You have to start moving around faster, right? So here's the same container with the same 8 atoms or molecules, except this time they're moving faster around because you've increased their temperature. When you increase their temperature, you give them more energy and they start moving around a little bit faster and they start pushing off of each other and they need a little bit more room, so they spread out, and that is its liquid form. Liquid. Okay, now let's say that we increase the temperature again. Oh man, it is starting to get warm in here. It is starting to get so warm, in fact, that I am moving so fast that you can't even see me. I'm just scooting right in and out of your frame. And boy, oh boy, the faster I move, the warmer I get, right? So we increase the temperature, and atoms and molecules, just like people, they start moving even faster. And that means they have to spread out from each other, and so they occupy more volume. And this, my friends, is the gas phase, okay? So back to the kinetic theory of matter, molecules and atoms are in constant motion, even when they're solids. And the higher the temperature, the greater their speed. The greater their speed, the more room they need, the more volume they're gonna take up, and that's where you get those phase changes, okay? So again, I like to think of it in terms of humans. helps me remember, what am I going to do at a greater temperature? That's kind of what the atoms and the molecules are going to do at a greater temperature. And that is the kinetic theory of matter. All right, in the last segment, I noticed that my figure was a little light green, so I redrew it here in black. Just to recap real quickly, a solid takes up a small amount of volume. We increase the temperature, which also increases the speed of the atoms or molecules, and they begin to spread out, just like people would if you increase their temperature or their speed, into the liquid form. Although the people, thankfully, wouldn't change into a liquid form now, would they? No, they wouldn't. But anyway, that would be called the melting point. Okay, and then with a liquid phase, increase the temperature and the speed again, and just like humans, they're gonna wanna spread out even more, occupy even more volume, and it becomes a gas. And this is the boiling point of a substance. Okay, boiling points and melting points always stay the same for each particular substance. So that's another way that you could identify something. If you didn't know what you had, but you knew its melting point or its boiling point, you could look it up and maybe narrow it down the choices. All right, phase changes in water. Moving on. Most solids, like we've been talking about, occupy less volume, a smaller amount of space, than their liquid counterpart, than their liquid phase, okay? But guess what? There's an exception, because it seems like there's always an exception to the rule, right? The exception is water. Water in its solid phase occupies more volume than its liquid phase. What? That's right. And thankfully it does. Let's read that one more time. Its solid phase occupies more volume than its liquid phase. So if you've ever gone to put water in an ice cube tray, who does that anymore? Not too many people. But if you have, in fact, tried to make your own ice, and once I did that, my kids were like, "What, Mom? How do you make ice?" Well, that's right. You just put liquid into the freezer, but you have to remember that when it freezes, the ice is actually going to occupy more volume, which is the exception to the rule. Its solid phase occupies more volume than its liquid phase, making ice less dense, than liquid water. Which means ice would float on top of liquid water, right? Other substances have a solid phase which is less dense, and so their solids would sink if introduced to their liquid phase. The solid would sink to the bottom before it started to melt, and then they would kind of even out. But water is the exception. And good thing, again, we can thank our masterful creator, because think of a lake. If a lake was to freeze and the ice was more dense than the water, the ice would sink to the bottom, or it would actually just start to form. Well, no, it would sink to the bottom of the lake, right? And then we wouldn't have this layer of ice on top of the lake, which means we couldn't go ice skating. No, there's a bigger problem with that, isn't there? Ice actually helps to insulate lakes during the winter and keeps those creatures and plants alive in the lake. So if the ice settled to the bottom of the lake and the water was no longer insulated, would fish be able to survive through the winter? Probably not. So thankfully the Lord created water to be the exception to the rule.